Here's our goal for this video. This unit kind of contains two ideas. One is understanding the general structure of the periodic table, and one is understanding something called periodic trends. This video is kind of going to serve as a bridge between those two concepts. I want to introduce some terms to you that you need to understand in order to understand periodic trends. So, in terms of your learning targets, the most important things out of this video are I can explain how electron shielding affects elements or atoms, and I can identify how main group elements ionize based on the periodic table. So you have to understand ionization and a couple of these other terms in order to understand trends. So here are your first two terms to understand: nuclear charge and electron shielding. These are two phenomena that occur in every atom that will affect our trends. So oftentimes when I ask the question, why is a trend the way it is, you will answer either nuclear charge or electron shielding. What is a trend in general? You'll get into that tomorrow, but a trend is as you move across the periodic table and down, something happens, and it happens consistently, and that's a trend. Okay, the trend that going down the alkali metals, they become more reactive, that's a trend. So, nuclear charge. You know your nucleus is positive. It contains protons and neutrons. As you increase your number of protons within that nucleus, you will increase your nuclear charge. And that addition of protons and that increasing of nuclear charge will affect our trends. The other thing that's going to affect our trends are electron shielding. So, as you fill up one of your energy levels, remember your energy level is essentially a row on the periodic table. Within each energy level, you have sub-energy levels like S, P, D, and F, but an energy level is essentially a row on the periodic table. And as you fill up one of your rows, basically all those electrons are acting as a shield from the attraction of that nucleus. So your nucleus is positively charged. As you increase that charge, you will increase the positive aspect of the nucleus, but as you increase your electrons, you will increase the shielding of that nuclear attraction happening. So you consider any atom, remember, your nucleus is positive, your electrons are negative. So part of just the structure of an atom is the fact that the protons are always pulling on the electrons. There is an attraction of the electron cloud with the nucleus. That attraction varies depending on how many protons are in the nucleus and how many energy levels are full. Okay? Nuclear charge, electron shielding. Again, you're going to use these to explain why the trends are the way they are. So what trends are we going to look at? We are going to look at these three trends. So you need to know what the terms mean before we look at the trends. Okay? So one trend we're going to look at is the trend of ionization or ionization energy. And ionization energy is the energy it takes to ionize an atom. Okay? So what does it mean to ionize? Well, ionizing is making it into an ion, which means doing stuff with your electrons. Specifically for ionization energy, it's the energy it takes to take away an electron, not to add one. Okay, so ionization energy is the energy it takes to remove an electron. And as we look at this, you'll actually see that there is a first ionization energy and a second and a third and a fourth for atoms, meaning there's an energy related to taking one electron away, which would be its first energy, and then there's energy related to taking a second one away and a third one away and a fourth one away. As you remove more electrons, the energy it takes will change depending on the atom. Okay. Another trend we're going to look at is a trend in electronegativity. So what is electronegativity? Electronegativity is a measure of the tendency or the ability of an atom to attract a bonding pair of electrons. Okay, this is just the weirdest one. Ionization energy is actually a measure of energy. It's in joules. It's an actual measurement. Electronegativity is this fuzzy kind of measurement because it's a tendency, the tendency of an atom to draw electrons to themselves. It's weird. And when I look at the actual numbers with you, when we look at trends, it's not the same as ionization energy. It's an actual, it's more of an idea of like a ranking, like, oh, this one draws electrons the most So we're going to rate that a 4. And then all the other atoms of the periodic tables are going to get different ratings based on the fact that the strongest pull gets a 4. Because nothing's physically being removed or transferred, it's a harder one to measure. And again, how this works is when we get into bonding, there's 2 different ways you bond. You either remove electrons and like take them as your own, or you have to share them. And the tendency to share brings in this idea of electronegativity, in that when they share, sometimes they don't share equally. Maybe one atom has more of a tendency or ability to attract a bonding pair to itself, okay? And that atom would be more electronegative. Okay, so the more electronegative atoms have a greater tendency to pull electrons toward themselves. Remember, electrons are negative, which means somehow there's a positive draw pulling electrons towards the more electronegative atoms. Atomic radius is the 3rd trend we're going to look at, and the atomic radius is the size of an atom. But if you really start to think about size of an atom, it's a strange thing because you can't really picture, right, protons, neutrons, electrons, and it's not super easy to measure the size of an atom. So if you actually look at the scientific definition of the atomic radius, you'll see that what they do is they take diatomic atoms, okay, and they measure the distance between the 2 nuclei of diatomic atoms. And once they measure the 2 distance, halfway between them would be the radius. Yeah, I'll show you a picture in a second, but your understanding can simply be that the atomic radius is the distance from the nucleus to our outermost energy level of the stable electrons, meaning not when they're jumping, right, but when they're in their stable configurations, it'd be to the outermost 90% probability electron would be there. That's the distance. Okay. How they actually do it is right here, as I mentioned. They take a diatomic atom. A diatomic atom is when 2 atoms of the same element are bonded, like if you have 2 chlorines bonded or 2 oxygens bonded or 2 hydrogens bonded. They take those diatomic atoms, they figure out the distance between the 2 nuclei, and then they half it, and that would be the radius. For ions, it's even harder, okay, to measure how big the atom is when it's ionized, meaning it's gained or lost electrons. This is usually done with crystallography. Okay, oftentimes ions make crystals, and they can actually look at the crystal structure using crystallography, and then sometimes actually measure distance. It's a lot harder, meaning our atomic radiuses are pretty right. We're pretty sure on most of them. Ionic radiuses, depending on what reference you look at, sometimes they're a little sketchy. Okay. So to understand ionization energy, you need to know something about ions. Yay, we finally get to learn about ions. You know already that for ions, it's gaining and losing of electrons. But this unit, you finally get to learn how atoms gain and lose electrons. Meaning, if sodium were to be an ion and it was going to gain or lose electrons, how many does it tend to gain and lose? There's one simple rule for ions. The goal of all ions is to gain and lose electrons to become like a noble gas. Meaning they want to lose electrons or gain electrons so that their electron configuration ends in P6. It's as simple as that. Okay, so wherever you are on the periodic table, you're going to gain electrons or lose electrons to be P6. There are 2 different ions we've already seen, positive ions and negative ions. You are never going to forget this again. I cannot believe I'm doing this on video for you, but you guys get this, so stick with it. 2 different kinds of ions, cations and anions. One is for the positive, one is for the negative. How will you remember this? Super simple. Cations are what positive ions are called. You ready? Cations, they're positive. You'll never forget it, right? Cations, they're positive, like paws, like cats. Cats have paws. Okay, you get it. Anions then are the negative ions. So cations are positive ions, anions are negative ions. If you look at your periodic table, how do you know what type of ion it will become? Okay. The left-hand side of your table, those ones are generally going to lose electrons and become positive. So your metals. Your nonmetals are generally going to take on electrons and become negative, meaning your metals are usually cations and your nonmetals are usually anions. Okay. Just take a look at them on the periodic table. Look at your alkali metals. We know that all alkali metals are the same because they have one electron in their s orbital. If they wanted to become like noble gases, they have two choices. They could lose one electron, or they could gain 7. Okay, one more in the S, and then all 6 in the P to become that P6. So if your alkali metals either need to lose 1 or gain 7, which do you think they're going to do, right? They're going to do what's easier. And it is easier to deal with 1 electron than to deal with 7 electrons. So your alkali metals, which all have the same configuration, right? They all have that S1. They're going to lose that electron and become a +1 ion. Your alkaline earth metals, remember they were all the same. They all had S2. They also have two choices. They can lose 2 electrons or they can gain 6. Same deal as alkali. The alkaline earth metals would rather lose 2 than gain 6. Okay. Meaning all the alkaline earth metals make a +2 ion. Moving across the periodic table, the rules for ions skip the transition metals. The main reason is that once we're in the D block, they want to be like noble gases, but they do their own thing. Okay, they have a D block now to deal with. So we basically skip the D block when it comes to creating common ions. I'll show you a little bit more of that when we do naming, but for now, you need to know the alkali metals form a +1, alkaline form +2. Move across the table to column 13. Column 13 with boron and aluminum. Okay, boron and aluminum, they are going to form a +3. They can either lose 3 or they can gain 5. And it'll still be easier to lose 3 than to gain 5. Then you go to carbon, silicon, and germanium. Okay, because I'm not going to deal with the metals. As I said, aluminum does this, so I talked about aluminum, but all the rest like tin, we're not going to deal with. But carbon, silicon, and germanium, they are now in this column where they could lose 4 or gain 4. There's no rule here. Okay, +4, -4 both happen just as readily. We'll talk about specific cases of when one will happen over the other. But for now, +4, -4, either ion is potentially possible. Move to column 15 with nitrogen and phosphorus and acetane. This column, now we're at this point where they can either lose 5 or they can gain 3. It's easier to gain 3 electrons than to lose 5. So as of nitrogen now, we officially have our anions. It's going to form a -3. Oxygen can either lose 6 or gain 2. It's going to gain 2 to be a -2. So that's oxygen, sulfur, selenium, like that. The halogens, okay, 17, they could either lose 7 or gain 1. They're going to gain 1 to be like your noble gases. So if you walk across your periodic table, column 1 makes +1. Column 2 makes +2. Skip to 13. Column 13, +3. Column 14, plus or -4. Column 15, -3. Column 16, -2. Column 17, -1. Noble gases. Are noble gases going to gain or lose to become like a noble gas? Right, they're good. So noble gases don't do anything. This is kind of the base of what you need to know in order to do the trends. You're ready to do form 2, and then from there we're going to move on to the periodic trends activity. Okay? Have an awesome night.